In this video, we will be talking about using chain rule and how to use it when calculating partial derivatives. Chain rule is a method used to derive equations that may have more than two terms or more than three terms, and it's basically just another way to use different sets of variables to solve different derivatives, right? So where you could start with two variables, x and y, you could further derive them with respect to functions of u and v, or t, or what have you. So it's basically just a way to visualize all of the components in one place. Okay, so for example, if we had function z equals a function of x and y, you would first derive partial derivatives with respect to x and y, and from each branch, you can derive with respect to u and v in that equation to get 4 different kinds of equations in total, right? It'll make a lot more sense when we see an example. So if we were to read from a chain rule tree, the sum of the products of a partial derivative along a first generation branch and a partial derivative along a second generation branch create the sum of our equation. So if we wanted dz over du, then we would use our function with respect to dx, then from there, dx with respect to du, plus our function dy, and our function of dy with respect to du. So if we wanted just our sum of u functions, we would go along this branch, and then we'd follow along this branch. So these would be multiplied, and we're adding it to this branch, following along to, this branch here. So hopefully that makes sense, because if you were to put these together, you would see that the dx cancels out and the dy cancels out. So then you'll just have your sum of your df over du, right? And that is essentially what this is asking for. Right, if you wanted to do v with the other hand, it'd be the same thing. You'd have your first function with respect to x or y, but then you'd go in the other direction to get over dv, so you're deriving with respect to v. Okay, so it'll make a little more sense in our following questions. So if we start with this function, so let w equal e to that power, right? So let's write that first one. So this is at the top of our tree. This is the most overarching one. Okay, so again, at the top of our branch, we are going to be using our original function, which is a function of x, y, and z. Okay, so this is our main function. So that means coming from this function, we're going to have one branch for each variable. And we are given what these will be. This is, so x is equal to, so let's start with x here, t plus sine 2t minus 2, y is equal to 3 minus 4t, and z is equal to 3e to the power of t squared minus 1. Okay, so in each intermediate step, this is where we have our dw as a function of dx. So this is our partial derivative with respect to x for this part. So if we were to do that, so only treat x as a variable, this is 2e, then that's 2x plus 5y plus z, right? Because y and z are remaining constant. And this here is 5e, 2x plus 5y plus z. And along here, this is just the same. Okay, so then moving on, if we were to now do with respect to t, since our only second generation branch is only going to have one variable because there's only, in each of our x, y, and z terms, there's only one kind of variable, which is t. All of these branches are going to just produce that variable t. So along each branch, this would be our previous variable and a partial derivative to t, so it's dy with respect to dt, and this is dz with respect to dt. So this is just a one variable derivation, so it should be a little easier to do. So then this becomes, so this is 1 plus cos, 2 cos, 2t minus 2. This one here is negative 4. And here we have 6t e t squared minus 1. Okay, so that is what our full chain rule tree looks like. So now we want to find what our value for w as a function of t. So that's the complete sum of our w over dt. So that means looking at what is in our green and our yellow. So if we started with this branch over here, this would be, so this is dw over dx in green, and this is multiplied by what we found here. So this is our dx over dt plus our second branch. So this is w as a function of y derived with respect to y. This is partial derivative of y with respect to t. And then this is plus in our last z branch over here, which is partial derivative of w with z, and then z and t. So all in all, this equals the complete sum of w with respect to t as partial fractions. So we're going to be using each of these green and yellow terms, right? And the complete sum will be dw over dt because, as we see, our x's, y's, and z's cancel. So it's just a complete sum of our function w with respect to t. So let's do just that. So I'm going to write this down here. Actually, before I even do any of that, I'm going to find our value of t. So we're given each of these red equations in our problem. And we want that t to satisfy each of our equations. Actually, sorry, this is a mistake. We're going to be using t to find our x, y, and z. So find x, y, and z with t. So in this question, we are given t is equal to 1. So that's what we're going to use. We're going to plug that in. So for our x variable, x is equal to, so we're going to plug in t, plus sine, and this is 2 minus 2, so sine 0, which means x is equal to 0 plus 1. So this is just x is equal to 1. So our first part. Then if we do y, so this is 3 minus 4. This is negative 1. And we have z is equal to 3e, and that's 1 minus 1. And this becomes 3e to the 0. And we know that's equal to 1 for our e. So this is equal to 3 for z. Okay, so these are the values that we're going to be plugging in once we solve. Okay, and now let's make our equation that we found up here. So we're going to start with Okay, what was it? It was 2, sorry, I need to zoom out a little bit. So we're going to start with 2e to the 2x plus 5y plus z. So this is our first term here. And we're going to multiply it with its derivative term, which is 1 plus 2 cos 2t minus 2. And that's our first term. And this is plus this term right here. So this is 5e to 2x plus 5y plus z multiplied by -4. And finally, this is plus, this is just e to the 2x plus 5y plus z. And this is multiplied by its derivative, which is 6t e t squared minus 1. So this is our complete partial derivative that we're looking for. And we're going to use this by plugging in our variables so we can get a final answer. So t was equal to 1, x is equal to 1, y is equal to -1, and z is equal to 3. So if we were to solve for this equation, this would give us, okay, so this is 2e, 2 times x is just 2, then that's -5 when we plug in our y, and z is 3. Okay, and then we have 1 plus 2 cos, and this is 2 minus 2 when we plug in for t, plus 5, and this is e2 minus 5 plus 3, then -4, plus e to the 2 minus 5 plus 3, and our last term, so this is 6e to the 0 when we plug in for t. So this will give us, so this is just going to be 2, because this is 2 plus 3 minus 5, which is 0. So e to the exponent 0 is just 1, multiplied by 2 is just 2. Okay, and then we're multiplying, so this is 1 plus 2, and then cos of 0 is just equal to 1. So this is just going to be 1 plus 2, which is 3. Okay, and our next term, we have just 5, and that's times -4. Here we just have 1, and this is times 6. Okay, so in total, our answer comes out to, so this is 6 minus 20 plus 6, so this is equal to -20 as our final answer. Nope, that is not how math works. Sorry, this is -18. Is it? No, it's not. Okay, so we have, sorry, -8. I apologize. Okay, so that is our first example with how to use chain rule. I'm hoping it's starting to make more sense. So the reason we only made one branch after our x, y, and z variables is because in each equation there was only one other variable to work with. So that was how we did that. So what if we had 4 different variables? So we had 2 original variables, x and y, and then we had 2 derived variables, u and v. What would that look like? Okay, so if we were to start with this one, we would start with z equals a function of x, y at the top. And we'd have 2 branches because we have 2 other variables, x and y. So we'd write what our x and y are, So this is x is equal to u squared v, and y is given to us as y equals v over u. Okay, and these each have two variables, so we're going to split these off into two. And this is going to be u and v, u and v. Okay. So this question lays out our data in a little bit of a different way. So rather than being given an explicit function, we're just given our function in a different form, where our partial derivatives with respect to our original function look something like this. So we could just write it in terms of our function in this notation. And once we have those, we can use what we already know about these two terms to derive them. So we can do this one easy because we're actually given an explicit function. So this is with respect to u, so this is going to be 2uv, and this is equal to just u squared. So this is like saying v and u to the negative 1, so this is negative vu to the negative 2. And then the other term is just going to be u to the negative 1. Okay, so once we have all of that, so we are given what our x and y, what our u and v are equal to. So if we take a look at this section here, we can find what our x and y is. So let's find x and y variables with u and v. So u is equal to 1. So that means x is equal to 1 squared, and times v, which is negative 2. And this is equal to negative 2. And then y is equal to, so we have v, so that's negative 2 over u, which is equal to negative 2 as well. So we want our functions to be for x negative 2 and y negative 2. So that means we can reject these terms right here and instead focus on using these ones in our equations. So if I were to write that out, sorry, let me just get rid of these so I have some room. Sorry, I'm just doing this to free up some space. So we want to find let's just focus on this one right here. So this is dz du. I'll let you guys do dz dv on your own after we do this first one. So this means that we are going to be going along our branch here and then going to our u branch. So we're going to start, so if I were just to write this out in terms of what we have, this would be, and then we said this was a function of negative 2 and negative 2, and that's just our x partial derivative, and that's going to be multiplied by our u partial derivative, which is u squared, so from this branch, and then this is plus our partial derivative of y from our original, where x and y are equal to negative 2, and then we're going along our u branch. Oh, sorry, this was our v branch. Our u branch is here, our v branch is here. Sorry, let me redo that. So this is actually 2uv. And we're going to use the left-hand branch for this one as well, which is negative v u to the negative 2. So when we plug in for our variables that we solved here, this is equal to, so if we take a look at our f of x partial derivative of x function, we see that it's equal to 3 when we have x is equal to negative 2 and y is equal to negative 2. So we're going to plug that in. So this is 3 times, and this is 2 times negative 2 times 1. And this is plus, and when we have our partial derivative y, where our x and y variables are negative 2, it is equal to 2. So this is 2, and this is negative 1. Sorry, v is negative 2. So this is negative 2 times 1 to the negative 2 squared, and this is equal to, so this is 3 times negative 4, that's negative 12, and this is positive 2, this is plus 4, so this is equal to negative 8 for our original function. Sorry, this should be dz along our u branches. Okay, so if I had more room, I would do the other one, but that works out anyways because I'd like you guys to do dz with partial fraction respect to dv on your own. And the answer for that one should be equal to 5. Okay, moving on. Okay, so now with our knowledge of partial derivatives, we're going to be introducing something called a gradient function. So gradient is used with this symbol here, p, where the original function is equal to the partial derivatives of that function with respect to however many variables it has. So in this case, we have 3, x, y, and z. At a certain point p, which is given to us as 1, 1, and negative 2. So these are our values of x, y, and z that we will be plugging in to get a real number from this equation. So this is a very simple example. So if we just start with this one, so we have capital F as a function of x, y, and z, which is equal to x squared, y cubed, z to the 4 minus 3, so 35. Okay, so then you're going to derive with respect to each variable like you're already used to. So we'll keep it separated by commas. So we can write it in this kind of form. So this will be 2x. In our first one, this is 3x squared y squared z to the 4. And finally, this is 4x squared y cubed z cubed. And we're going to do this at point 1, 2, and negative 2. Okay, so when we plug in for those values, this gives us, so this is 2, and z was equal to negative 2. And this is 3x squared, y squared, z to the 4. And this is 4x squared, y cubed, and z. This is negative 2 cubed. And once we plug those values in, our gradient has 3 terms separated by commas, which is, so this is 2 times negative 2 to the power of 4, and this is 32. Sixteen times 3 is equal to 48. And in our last one, this is going to be, so that's negative 8 times 4, which is negative 24. Right, so that's just another way we can use and apply partial derivatives. Okay, so next we're going to be talking about equations of planes. So as a remark, an equation for a plane looks like this form here, where a normal line is a vector that passes through, so that's perpendicular to a surface, and it's passing through a certain point given here, and we'd use this equation to define it. So it's the dot product of our position times our normal vector, and it's equal to the original position of the dot product of our normal vector. Where this first r here is a function of x, y, and z. Okay, so we just talked about the gradient, so that's taking the partial derivative at a certain point. And this is just a geometric interpretation of what that might look like. So if we have a surface here, and given by this equation, if we make that equation equal to 0, and let this P be a point on the surface as shown, it follows that a vector that's normal to the tangent plane to surface S at that point P is the same thing as our gradient. So basically this represents a normal to our tangent plane. So if we make a tangent plane to our point, right, this normal vector comes out of that plane that we just added. So that's how we could use our gradient, where our gradient is equal to our normal our normal vector from our tangent plane. Okay, so if we were to apply this, so let's find an equation of a tangent plane and normal line to the surface. So this is xy plus xz plus yz equals negative 3 at our point 1, 1, and negative 2 on our surface. Right, so this represents our function for our gradient. So to start off, we know that this function, this surface, must equal 0 in order for us to use this rule that our normal vector is equal to our gradient. So we just have to move things around. So that means we can just move this 3 over, so it is equal to 0. And this is plus 3 now. So we know that our gradient, let me redraw this. So we know that our gradient for f at a certain point P is equal to, so our function with partial derivative of x, function and partial derivative of y, and our function partial derivative of z at a certain point P. So if we were to do this, I'm going to do this in a different color now. This is going to be, so our first one is y plus z, and this is 0 because this is not including our x as a variable. So that's our first one done. Our second one is x. This is 0, so we don't include it. And this is plus z. And finally, with respect to z, this is x plus y, skipping the first term. And it's at point 1, 1, and negative 2. These are the values we'll plug in. And this means gradient is equal to, so y is 1 plus z is negative 2. So this is negative 1. This is also going to be negative 1. And this is going to be 2. Okay, so that is it for our normal. So let me just replace that. This is our normal vector. And going back a couple slides, this is the equation that we use to define a tangent plane. So if we were to write this out, so this is r times our normal plane is equal to our point. So this is r naught, which is equal to our point here, the dot product of our normal vector. So this r here is just going to be x, y, and z, just a function of those. And multiplied, we already solved for our normal vector in our previous question. So that is negative 1, and 2. And this is equal to our point P, because that is our initial starting position. And this is multiplied again by the normal vector that we just solved for, which is negative 1, and 2. Okay, so if we do that, we'll have negative x, negative y, plus 2z. This is equal to negative 1 minus 1 minus 4. Okay, and if we move things around, this will give us x plus y. And this is minus 2z. And over here we have negative 6, so then we move that over. Actually, no, that stays on that side, so this is negative 6 is equal to 0. So this becomes the equation for our tangent plane. Okay, so let's do another example. I'm going to color code it a little better. So we'll start with blue over here, and our point is going to be highlighted in red. Oh, sorry, I believe this is the same question. Sorry, this is the same question as the one that we did before. So I'm going to find us a different question that relates to this topic. Okay, and we'll go through a couple other examples. Okay, so find an equation for the plane tangent to this surface here. So let's work with this question here. Okay, so let's start with question 1. Okay, so we are given actually let's work with question 4. Okay, so 4 is most similar to what we just worked with. So we have an equation, so it's already equal to 0, so that's awesome. So we can just work with this right away. So our normal is equal to, so we'll do it with respect to x first. This minus y squared plus 3z squared. And this is just going to be a constant. So we leave that there. Actually, since these are constants, these go away too. Sorry, forgot about that. And this is negative 2y. And plus our z term, so it's 6z. And we are using a point 1, negative 3, and 4. So let's find our normal first. So this is equal to, so we plug in for x, this is 8. Plug in for y, this is 6. And plug in for z, this is 24. Okay, and now when we use our tangent plane, our equation is r times the n that we found, and this is times our point. And then that's dot product of the n that we found. So this is x, y, z, dot product with, so this is 8, 6, and 24. And this is equal to our original point, which is 1, -3, and 4. And this is taken with the dot product of our normal vector, which is 8, 6, and 24. So then this gives us 8x plus 6y plus 24z, and this is equal to 8 minus 18 plus 24 times 4, 96. And this gives us, if we move everything to one side, plus 24z. This is 8 minus 18 plus 96. And we move this over, this is negative 86 equals 0. And that is our equation, and let me check our answer. And we can reduce this. So this is correct, but we can reduce this to be, so each of these terms is divisible by 2. So this can give us 4x plus 3y plus 12z minus 43 is equal to 0. Okay, so that is another example. We're going to go through a couple more afterwards. Let's finish up what we were talking about in our notes. Okay, so next we're going to talk about increments and differentials. So increments or change in independent and dependent variables. So the increment or change in the independent variables x and y are respectively denoted and defined by delta x is equal to our new x, so our final x minus our initial, and same goes for our y, final minus initial y. And the corresponding change for dependent variables, so if we have a function with respect to some other variables, our change in z would be our change in our function, which is our new function, so our final function minus our initial function value. Okay, so if we were to take the increment differential for this one here, our df is defined by times dx, so our partial derivative with dx, multiplied by dx, and this is plus partial derivative with dy times dy. And you can see that these two would cancel out, so those terms would cancel, leaving just the df at the top. Right? So if we were to write this out, this would equal, so we'll start and derive with respect to our x. And this is plus 2y dx. And this is plus, so this is y squared x squared plus 2x dy. And since we're not given terms or values to plug in for x and y, we would just leave it in this form. Right? So we don't have to do any more work after this. Okay, so what happens if we're given a problem where we have to apply this to real-world examples? So the volume of a right circular cylinder has a radius r and a height of h and a volume of pi r squared times h. So this is h and our radius is r. So use differentials to determine how many cubic centimeters the volume changes if the radius is changed from 10 centimeters, sorry, it got cut off, to 10.2 centimeters. And if height changes from 5 centimeters to 4.95 centimeters. Okay, sorry, let me just get rid of this altogether. So how would you start to approach a question like this? So our approach to this question is very similar to the one above, right? But instead of using these n terms here, these are going to be replaced with our delta x and delta y variables. So let's just solve for those first. So delta x is equal to, so our final minus our initial. So this is our final, so let's start with radius first. So our radius went from, so that was 10.2 minus 10, so this is 0.2. And our delta h is equal to, so then that's our final minus initial, so final is 4.95 and minus 5. And this should give us a negative 0.5, 0.05. So those are the first ones. So these are going to be capping off our differential. And we're going to find our differential in the same way. So volume is equal to pi r squared h. And so if we were to take the change in our volume, we would start with dv dr times our delta r. And this would be plus our dv dh times our delta h. Right, so this is similar to related rates from Calculus 2. So if we were to derive this equation just with respect to r, this would give 2r pi h. And this is times our 0.2. And then we have plus. So now we're going to use dh. This just gives pi r squared. And this is times our delta h, which is negative 0.05. Okay, and we're going to plug in for our initial values. So let me just write that. So plug initial radius and height. And this will give us, so delta v is equal to, so it's 2, and our original radius was 10, pi stays the same, and our original height was 5 centimeters, this times our 0.2, and this is plus pi, and our initial radius, again, was 10 centimeters squared, and this times negative 0.05. So if we plug all of that in, our change in volume is equal to, so this is 2 times 10 times pi times 5 times 0.2, and this is plus pi times 100 times negative 0.05, and this gives us a value of 47.124. And this is in centimeters cubed because we are working with volume. Right, so that is how to work with problems like this. Let's see if we can apply it to this example here, where we are working with resistance. Okay, actually, I'm going to be skipping this question. We can return to it in the next video if I remember to. I'd like to just finish the notes section of this. So next we're going to talk about linearization of several variable functions. So it's similar to linear approximation that we did in Calculus 2. And we're going to be using this main equation here. So we're going to have our original function with our original values of x and y. All right, and this is plus our partial derivative of our function times our, with our original x and y variables times our change in x, and then with our partial derivative of our function with respect to y as a function of our original x and y values times delta y. Okay, so if we were to use this example and linearize it, so find the linearization of f at p. Okay, so we're going to start with our original function, so this is equal to, so we have our original function, so that is ln x squared plus y squared plus xy. And this is plus our derivative. So when we take a derivative of ln values, this becomes, so our derivative is on the top. And this with respect to x first. This is over our original. And this is plus now with respect to y. So this is, sorry, this is not supposed to be here. So x squared would be treated as a constant, so that's 0. So we have 2y plus x over x squared plus y squared plus xy. And if we plug in for our original values at this point, oh, sorry, hold on. And this is supposed to be delta x and delta y. Okay, so let's write this out again. This is 2x plus y over x squared plus y squared plus xy. And our delta x, which is equal to x minus our given point here, and this is plus 2y plus x over x squared plus y squared plus xy, and our delta y, which is y minus -1, which is plus 1. Okay, and we're going to plug our point, right? So this gives us, so this is 1 plus 1 plus -1. So this is ln of 0, right? Sorry, no, this is ln 0, not 0, ln 1, right? Because we have 1 plus 1, so that's 2 minus 1, so that is 1. Sorry, ln of 1 plus, so we have 2 plus 1, so that's 3 over, then x squared plus y squared, and this is 1, it's x minus 1, and this is plus, so 2y plus x, so this is -2 plus 1, so it's -1. -1, sorry, this is supposed to be 2. No, it isn't, hold on. So this is 2 minus 1, this is 1. Okay, and this is with x plus 1. So then this is going to give us 0. And this is plus x minus 1. And this is minus y plus 1. And finally, this will give us, so our linearization as a function of x and y is equal to x minus y, and then that is minus 2. Okay, so that is part 1 of our question. Okay, and this is the last part of our video, so we're going to do part 2. And so use part 1 to estimate the value of this new function here. Okay, so now we're going to take our original ln function and we're going to plug in our new x and y values. So our x value now is 1.05 squared plus our new y value is negative 1.03 squared. And this is plus 1.05 times negative 1.03. And this is roughly equal to the approximation that we got for our linear approximation, which was x minus y minus 2. Let me just plug those values in. So this is x, it's 1.05 minus y, and minus 2. So let's calculate this. This is ln of, so this is 1.05 squared plus 1.03 squared plus 1.05 times 1.03. Oh, sorry, this is supposed to be minus. And this is supposed to be 1.0819. And this is equal to, so using our other side, this is 1.05 plus 1.03 minus 2, and this is 0.08. Right, so that would be our answer for this part of our question. All right, so that brings us to the end of the note section of this video. In our next video, we're going to be going through some more examples that relate to the topics we covered, which is chain rule, tangent planes and normal vectors, our gradients, as well as increments and linearization. So we're going to cover all 5 of those topics in our next video with some examples. Thanks for watching.